Hi everyone, welcome to the sixth episode of the Machine Learning at Helmholtz Zentrum Gestalt Machine Learning Seminar. It's a beautiful Tuesday with sort of unpredictable weather in Hamburg. We've had a bit of rain, a bit of sun, and this fits our topic really well. We're going to cover predictability, a problem partly solved by Lorentz. It's often referred to as the Lorentz 1996 model, although the paper seems to have come out in 1995. It's a really interesting model where he covers the question of predictability of the climate, especially of the atmosphere. He's interested in how small errors arising from observations or calculations will grow over time as we attempt to make predictions, and how this puts fundamental limits on our ability to predict the system. I can't stress enough that it's really worth reading this whole paper. It's beautifully written, it's very approachable, it covers a lot of different concepts, and it gives a nice contrast, to where we're at now, and we see where we've come pretty far in the past 25 years in terms of computation, in terms of predictability, and where we maybe haven't come so far. So the structure of the seminar today is we're going to break it up into little parts. I'm going to cover the overall paper really briefly. We'll see what model he's introducing, why he's interested in it, what are the basic concepts. Then Marcel Nonnenmacher is going to talk about how this model has been used to identify unknown parameters of models. So if we have some model parameters that would affect the simulation outcome, then how can we identify them from simulator outputs? So he'll cover a few of these approaches, including his own work. I'll then briefly talk about a confusingly named parameterization. So as opposed to parameter tuning, where we want to identify unknown constants in the model itself, parameterizations are where we're trying to approximate some unresolved process with a mathematical formula of some kind. And I'll talk about what these are, how they've been used and tested on the Lorentz 96 model, and ultimately how machine learning can play a role there. And then finally, Tobias Finn will talk about stochastic or random parameterizations, basically using randomness to describe deterministic but chaotic systems. And he'll run us through a paper that takes this approach really nicely. Okay, so predictability. Lorentz gives a few examples in the paper of some more or less predictable systems, right? So as an example of a predictable system, he considers the tides, the ocean tides, right? We can make a pretty good prediction of what the tide is going to be years in the future. And in fact, we don't actually have to look at the state the tides are in now. And that's because the tides are mainly forced by these external factors, the gravity of the moon, the gravity of the sun, and basically we don't have to look at the initial state of the system to predict the future state. And then in contrast, the atmosphere is something really, really different. And it's something where we do need to look at the current state if we want to make a future prediction. And this makes it a much more difficult problem. So he's interested in how well we can predict this future state. And the key quantity he's looking at is something like the way the error grows at the doubling time. I'm going to read a small quote from page 4 of this predictability of problem partly solved. So he's talking about pairs of states of the system, states of the atmosphere, or ultimately states of the simple mathematical model he's going to introduce. Our interest in pairs of states arises from the case when one member of a pair is the true state of the system, while the other is a state believed to exist. Their difference is the error in observing or estimating the state. And if the assumed state is allowed to evolve according to an assumed law, this will be the simple mathematical model we'll identify shortly, or the laws of fluid dynamics and other physics for the atmosphere, so that the assumed state is allowed to evolve according to an assumed law, while the true state follows the true law, their difference becomes the error in prediction. In the meteorological community, it has been common practice to speak of the doubling time for small errors. This is inversely proportional to lambda 1, that is the first Lyapunov exponent, which we'll explain shortly, in the case where the assumed and true laws are the same. So what's he saying here exactly? We have a deterministic dynamical system where the system state evolves forward in time according to some differential equations. And what he's saying is if we have two different initial states, the difference between them arising due to some error in our previous calculations or our limited fidelity in our observations of the system will grow over time. And then he wants to measure, how quickly will it grow? So, of course, it can't grow infinitely, but because the system itself is bounded, right? So the error in, say, an estimate of the temperature or the pressure in the atmosphere or the wind speed is going to be bounded by how large these values can be in the first place. So eventually, it'll grow and grow and grow these errors, but as we try to make more difficult predictions further and further into the future of this chaotic system, but it can't grow infinitely because at some point it just reaches the same error as if we just choose two different random time points and try to guess one from the other. And so when we say it's a chaotic system, we mean precisely this increase, that if we make a small perturbation to the state of the system, that this perturbation will grow over time according to the differential equations describing the rules of the system. So Lorenz wants to study this phenomenon. He wants to study it in the atmosphere, the ocean, and so on. He wants to come up with a simple mathematical model exhibiting these properties, which is easy to run in terms of computation and easy to analyze in terms of mathematics. And so he comes up with a simple mathematical formula for the system state, which I'm going to explain really briefly right here. So the idea is the state has k different variables. You can think of these as almost like grid cells in a climate or weather model, but they're only on one dimension, let's say east to west, which goes around in a circle. So we have x1 to xk, where k is the number of different, let's call them grid cells on our one-dimensional grid. And in the applications run in this paper in the 90s, k might be anywhere between 4 and 36. So you have these different variables, which are sort of supposed to be very crude proxies of the state of the atmosphere. And we have a rule for how each one changes over time. Now, how do they change over time? So we have this term here, the rate of the little kth grid cell, its change is going to be inversely proportional to its own value. So this is kind of a dissipative system where it'll sort of forget things over time. It's like exponential decay. It is got some external forcing. And then it's got these nonlinear terms, which are products of the neighboring grid cells. And this is a very crude mathematical model, he says, for advection. So there's some interesting language he uses to describe this, and it's worth kind of unpacking it a little bit and saying what it means. The physics of the atmosphere is present only to the extent that there are external forcing and internal dissipation simulated by the constant and linear terms. So what he's saying here is that if we ignore all the nonlinear product terms, then basically each x will decay exponentially to the value of f, the forcing. The quadratic terms simulating advection together conserve the total energy, which he considers as the sum of the square values of all the x's. So what is he actually saying? This is a bit abstract. Well, conserve the total energy means that if we take up all the values of these abstract variables, which you can think of maybe as temperature or moisture or pressure in these different grid cells, if you think of all of these, if you square the values and add them up, then you get something like an energy. And if you only look at the nonlinear product terms, you apply the chain rule, to look at the derivative of this energy, you can see it's going to be the sum of 2 times each one times the derivative. And if you do all the math, it turns out that this comes out to 0. So the derivative of this quantity is 0. In this sense, is something roughly abstractly like an energy preserving system. So it has some of the mathematical and conceptual properties of the real atmosphere, right? It forgets things over time, but it preserves other quantities over time. He describes the phenomenology of this model a little bit. For small values of f, it decays to a steady state solution. When it gets a little bit larger, then they get periodic. And as they get larger still, it becomes chaotic, these different forcing terms, right? So he plots some of these. You can see this quasi-periodic. These are, if we look at one of the grid cells over time, we get these curves here. If we look at the whole system state at different times, we get these curves here. I'm going to borrow this really nice animation that was made by Stefan Rasp to describe this system. You just pull it up, if I can find it. So we can actually see an animated version of the whole thing in right here. So here we have the original version.
Seem to have lost screen share.
I'm sorry? Oh.
Your screen is...
I am terribly sorry. Thank you very much. And briefly cover the material that I should have had on my screen. So very briefly, equation 3.1. We have...
I do not see your screen.
You do not see my screen still.
I still see your name.
Let's see if we can resolve this. Okay, is my screen visible?
Yes.
Okay, thank you everyone on Zoom chat. So yes, we were broadcasting this to YouTube, and if you want to tune in there, you can see what was missed. Apologies for that technical problem. So we have our equation here. These are our a set of different grid cells coupled like this. We have our forcing term, our dissipation term, which causes the system to forget things over long time scales, and we have this nonlinear advection term, which we can also look at the indices and see as asymmetric. It has a certain west to east or east to west tendency for things to flow in a certain direction. And now I'm going to show an animated version of this, which gives a sense of what the model actually does and what it looks like. So this is from Stefan Rasp, this animation. And you can see the different values. Here this is done with k equals 36 different values. You can see we have these peaks that kind of move around and respond nonlinearly to the peaks around them. So this is kind of the simplest possible mathematical model that Lorenz wanted to use to describe predictability in something that captures some of the core conceptual aspects, of the atmosphere. Okay, so this is the state if we look at one of the grid cells over time right here, and these are the state of the full system at different times. Okay. So moving a little bit further along in Lorentz's paper, he did some really interesting numerical experiments by simulating from these differential equations. So he just integrated them numerically and looked at what happened. He started with, as he said, pairs of different nearby system states and observed what happens to the error between them as he solves them forward deterministically in time. And so if we look in the top graph here, we have here on a linear scale and here on a log scale. And this is an average of 250 different runs with nearby initial states. And we measure the distance in between them. And we can see, looking on the log scale, with the axis on the left, we can see that it pretty much grows linearly, showing some kind of an exponential growth of the errors. And what we see in both cases is that eventually the errors get so large that it's as if we just chose two random states from a long-running simulation, and then the error saturates and can't grow any bigger. But that basically, when we try to make predictions at this long range, that it's pretty much just like guessing. And so it's worth asking, and Lorenz does ask in this paper, where do these errors come from? One could be that we make an observation of a physical system that has observation noise. The other is we have many steps in our prediction routine, and these steps also introduce error. And anytime one of these steps introduce error, this will also affect the predictability of the system in the long term. Another key point that Lorenz stresses in this work is that predictability really depends on the setup of the system. So here in the top graph, we're seeing if the error starts out very large already, then it grows and then it saturates pretty quickly. This is with 4 grid cells instead of 36, so that they could do 1,000 runs in the 90s. Here we see with 4 grid cells and a smaller initial error. However, for the third curve here, what they've done is reduce the forcing term. So the system is no longer in the chaotic range, it's simply going to be periodic. And when this happens, we see an initial increase in the distance between the two initial states, but then it goes back down and saturates, which means we are able to make predictions far, far into the future, despite the fact that you have an initial divergence of these model states. So what is he trying to say there? He's trying to say several things. One, the predictability of the system can really depend on the setup. Two, the validity of this idea of the doubling time has to come with a number of caveats. In some cases, it makes a lot of sense. We double, double, double until we saturate. We can't increase our error anymore, and that's it. In other cases, it makes no sense. When the system isn't really chaotic, the errors won't double forever. And then this is not really the right way of describing the system. So this is a start that Lorenz makes. He then goes back to kind of the concepts of what he wants to predict in the atmosphere, and this leads him to modify the model. I'm going to jump ahead to page 11 in this PDF, and I'm going to read another little bit from his motivating, here's page 11. So he's interested in the case of what's happening on different scales. The relevance of the Lyapunov exponent is even less certain in systems such as more realistic atmosphere models or the atmosphere itself, where different features possess different characteristic timescales. In fact, it is not at all obvious what the leading exponent for the atmosphere may be, that is, the doubling time, how quickly these errors grow, or what the corresponding vector may look like, which is to say, the kind of errors in space, the spatial patterns which grow most quickly in their error. So the perturbation over the whole field, which would cause the error to increase most quickly. To gain some insight, imagine a relatively realistic model that resolves larger scales, planetary and synoptic scales, so large weather fronts and storms, and smaller scales, mesoscale motions and convective clouds. Forget about the fact that experiments within a global model with so many variables would be utterly impractical. Convective systems can easily double their intensity in less than an hour, and we might suppose that an initial error field consisting of only of the omission of one incipient convective cloud in a convectively active region, or improperly including such a cloud, would amplify equally rapidly and might well constitute the error pattern with the greatest initial growth rate. So he's saying if you make a perturbation to a local convective system, then you might get a storm breaking or you might not. You might get it growing very quickly or you might not get it growing so quickly. And so this is what will describe the initial phase of error growth and the short-term predictability. But then he goes on to say, this growth rate need not be long-term because the local instability responsible for the convective activity may soon subside whereupon the error will cease to grow. So the storm breaks or it doesn't break. But whatever happens, it's not going to affect too much the weather in 3 days, 4 days, or in places very distant. It's just one storm system. It's just one cloud. A pattern with convective scale errors, so these small scale errors in clouds, distributed over many regions then, would likely grow more steadily. So if we have errors distributed over the whole globe or a large region, then this might cause changes in long-term predictability, whereas short-term errors will cause, when they may grow in the short term, but eventually they're going to fizzle out, right? That they're not going to affect the system on a large scale over a long time. So the idea being that some of the small scale errors will average out and not affect the large scale. So in order to investigate this kind of coupling of fast and slow, of large scale and local, he extends his model to have a slow, large scale, and variables which are just exactly like the ones before, right? The x's, and now we're adding in y's, and y's are going to be a lot more of them, right? So for every x, you're going to have several y's. So it's like these little mini grid cells that live in each x grid cell. Again, on the same one-dimensional periodic axis. The y's also have an asymmetry, but they tend to flow in the opposite direction as the x's. We'll look at a video in a second. And they're coupled, right? So the change of each x is going to be affected by the average value of its small variables, the y's. Also, the change of each fast variable, the y, will be affected by the value of the slow grid cell variable that contains it. So let's have another look at Stefan Rasp's animation. And we will have a look at the complete two-level Lorentz 96, where we can see the fast and slow variables evolving side by side. So here's the full set of equations. And here's what the full model looks like. So we have the slow variables in blue, the fast ones in orange. And each one of these slow variables is going to be affected by all the fast variables nearby, and it's going to affect them in turn. This is the extended version. Okay. So now he can repeat his previous analysis. This is Lorentz's graphs of the same phenomenon, right? Here we have snapshots of the system at different times. But he can repeat his previous analysis and look at how quickly do errors grow in the fast and slow variables. Here, in figure 3.4 of the Lorentz paper, is the rate of change in the large scale variables in A and the fast scale variable, the fast fine scale variables in B. So what happens? We start off with a very small error in both. Then the first thing that happens is the small scale variables, the orange ones from the animation, are going to increase their error much more quickly. And it's only once they've increased their error significantly and the pair of simulations have diverged completely in the value of the quickly changing small scale fast variables, this causes changes in the slow scale variables as well, this other curve. But we also see that the errors arising from the fast variables saturate much more quickly. At a certain point, they're completely random from one state to the other, right? They've completely diverged, but the two simulations have not at all diverged in terms of the slow variables, right? So that means some of these processes are totally unpredictable. What's happening on these fine scales, kind of like trying to predict the weather in 3-4 weeks down to the hour in Hamburg. But the slow scale variables, trying to predict something more like seasonal or yearly effects, there the predictability isn't completely lost. So Lorentz has extended the model to capture these two different effects. And so I'll just read one more quote from the paper as he sums this up. We now see the probable atmospheric significance of the error doubling times of the various global circulation models, which, as measured in those days, were a couple days. Each doubling time appears to represent the rate at which, in the real atmosphere, errors in predicting the features that are unresolvable by the particular model will amplify. After the errors that are resolvable by the particular model will amplify after the errors in unresolvable features have reached saturation, right? So for a slight perturbation of the model state, first the fast features will diverge, and then this will cause the slow features to diverge. Before accepting this interpretation, we must recognize the possibility that some of the small-scale features will not saturate rapidly. Possibly they will act in the manner of coherent structures. So he's saying that just because the quickly changing fine-scale features in his model quickly lose predictability, it's not necessarily the case for the real atmosphere. So summing up, we've built this model which exhibits a lot of the interesting features of the real atmosphere from a mathematical perspective, while being much simpler computationally and mathematically. It has some unknown parameters describing the forcing, describing the coupling between the fast and slow variables. It has the ability to forget some things while remembering others. It has different aspects which have different horizons of predictability. And so it's been used for a lot of different applications in neuroscience to develop algorithms and to test different tools. So one of these is the task of estimating the unknown parameters of these models. So I'm going to turn over to Marcel Nonnenmacher now, who's going to talk about some papers which have investigated this problem. I think, Marcel, you're going to look at some deterministic as well as Bayesian estimates. Okay.
So can everybody see my screen?
Yeah.
Okay. So as David already mentioned, I'm going to talk a bit about inferring parameters on the L96 model as an example. So we've already seen these animations. Stefan Rath has this code online where you can just set the 4 parameters of the model. So these are the typically studied values because in this setting, the model behaves chaotically. You can just execute this, which takes a few seconds. Actually pretty quick. Part of this is just delay because I'm running this on my cluster. And then if you take a single snapshot, you get a certain pattern of the output that is characteristic in a certain sense for this parameter setting. If you go to very different parameters, like if you increase the external forcing by a factor of 2.5, you get different model output. You can do this with the other parameters as well. So here I've weakened the interactions between the fast variables to the point where they essentially just follow the coarse variables, and there's not much going on between them. And you can also play with the other parameter here, the C parameter, which is the coupling between X and Y, and set that really high. And then you see that also there is, similarly to here, there's a much closer following between the 2 different variable groups. You can also do something funny, and you can invert the sign of the interaction so that these things don't follow each other, but they avoid. So this is in the forward mode of operating the model. So you set some parameters. In this case, we've set pretty strong deviations from the standard regime, usually by a factor of up to 10. And then you get very different results. So this is nice for studying. This is nice for thinking about what the model does and how it works. But if you want to use these models to compare it to data, you want them to produce realistic results. And often you want them to produce results that match some observations. And I've done very, very extreme changes, and we saw very clearly that the results weren't matching the data anymore. But if you change something on a smaller scale, like here, I increase one parameter by 20% and I decrease another one by 20%, then you can get stuff that isn't so immediately clear that it's different, at least to the bare eye anymore. And then you really go into the question of, given some observation, which of the two parameter groups in this case might have actually produced the result, right? So parameter inference is a very big thing in machine learning. Here's some slides, let's go to the top. Where you generally have a setup where you have some sort of model, you give it some parameters, and then comes out some data, and then you want to measure, you want to match that to actually measure data. And remember, we're talking here about this toy model, so no one's probably ever going to fit the L96 any kind of measurements in real life. But we just want to think about the idea of how you would fit the parameters of a model of the type of the L96. And the difficulty here from a machine learning perspective is that the forward model is formulated in terms of differential equations, which actually have to be integrated. So what is classically the case in pure machine learning is that somebody has some analytical function, say of the forward probability densities, where for every parameter setting, it gives you how probable, how likely are we to observe a certain simulated or observed data set, and then you can differentiate this through this from the mismatch between data through the model back to the parameters. With these kinds of models, it's a bit more tricky because the forward model block is often not differentiable. There are some ways of getting around that and make it differentiable. But this usually involves a lot of work. So how do you do parameter inference for these kind of models where you want to get measured data to match the simulated data? And for this, you need to choose the right parameters. So one paper that did this, that looked at this, we're going to start with this one. So there the idea is that if you look at the phase diagram of a couple of, I think the first three in this case, of the resolved variables of the L96, you want to fit the parameters that have, you want to find the parameters that were used to simulate this, such that if you were to produce more simulations with this parameter setting, you reproduce this. And here in this case, they learn the parameters from both the resolved and the unresolved parameters. And on the right-hand side, you see that it actually also works to learn the parameters just from the fast, from the unresolved variables. If we jump to the paper, so just to get the authors. So this is a recent paper, 2019, that uses deep learning and neural network approach to do this. So rather than writing down some probabilistic model for the forward equations, their approach is essentially direct regression, where they choose some parameters, they do the forward integration to get a result, which is a state trajectory of the resolved and the unresolved variables over time. And then they do a regression back from X and Y into the parameters from a lot of X, Y, and parameter pairs. So just in this case, so they choose a lot of parameters, which you can see in the left box, and they do a lot of simulated data, and then they learn a regression back from the simulated data into the parameters. And then they can, into that regression function that they learned, they can plug in the measured data for the measured data, go back to the parameters. And this way you avoid this non-differentiable forward block. Now, how do they do this? It's essentially all described in this part here. So they choose 200 different parameter settings. So these B, C, and H parameters. They only do 3 out of the 4. And for each of these 200, they simulate 50,000 time steps. And it's a 20-dimensional system because in their case, they choose 4 of the resolved variables, and for each of them, 4 of the unresolved ones, for in total 4 times 4 equals 20. Now, this would give you a training data set of only 200 pairs of XY on the one side and parameters on the others. So you would learn the regression from X and Y into the parameters from 200 data points, which if you want to do a deep learning approach is a little few. So what they do is they break these 50,000 sequences into smaller chunks of 20 by 20. So it still has all of the variables, the resolved and the unresolved ones, but it's only a length 20 time sequence. And the hope is that these are long enough to identify all of the parameters, and that by chunking it up into these parts, you generate enough little chunks to train a neural network that can go from these 20 by 20 chunks into the, in this case, 3-dimensional parameter vector that you're trying to identify. Now, if you have these 20 by 20 chunks, and you're thinking of doing with deep learning, one thing you can still buy, so here's a linear model baseline. So these are the results as they're often portrayed in machine learning papers. You just have columns for losses for different settings, and then you want your loss to be particularly low. So they have a baseline of a linear model that they train from to regress from the observed, resolved, and unresolved variables into the parameters. They have a training loss, and the column we care for is test loss. So a linear model that tries to map from these 20 by 20 patches into the parameters of the L96. This is pretty bad. And then they have 3 different deep learning architectures. One is fully connected, which just learns a mapping from these 400-dimensional vectors, these 20 by 20 patches vectorized into the 3 numbers. And then they try out a 2D convolution, which does just an image convolution with some small convolutional filter of the 20 by 20 patches. But because they're 20 by 20 patches that they're using on, one is time and the other axis is space, they also try out a version where they do 2 stacked 1D convolutions. So if you think of sorry, I jump ahead, but I have a little. So if you think of this being the data where their 20 by 20 patch would be the number of variables of the L96 model by time. So this is not 36 by a lot. But if you think of this as being 20 by 20, then you have 2 different axes that mean 2 different things. So one thing they tried as well is to do a 1D convolution across time to essentially get rid of the time dimension first, and then they do a 1D convolution across space. This is something else they tried. So overall, we had fairly similar results for different approaches. They have a little distinction between cases where they do include the test data parameter sets already during training. Remember that they have only 200 different parameter sets, even though they created a lot of data points by chunking up the long sequences that they generated. And the distinction from a machine learning perspective doesn't make too much sense. Let's glance over it. But what they do get, as you can see here from the reconstructions, is that if they learn this regression and then for a fixed simulation with fixed parameter sets, if they then simulate again with the parameters they've learned, then they can match the data. So the simulated data matches the original data. So this does work from a pure regression point of view, where you try to just regress back from simulation output back onto the data. Okay, to my little presentation, not trying to spoil everything. So that's a point estimate. So what you're gonna get for every of the observed data, you're gonna get one estimate of a parameter, and then you can forward simulate again. But as we've seen before, if I may quickly bring this up again, there's not always perfect clarity which parameter produced which data set. In particular, if your forward model includes noise, or if it's working in a chaotic regime, if there's tiny differences in the initialization. So for instance, if you look at these two parameter settings that I just cooked up myself before, this one and this one, and you look at the corresponding outputs being fairly similar, at least to my eye right now, you could imagine that if you were to observe this data point, you might say like, maybe it was this parameter setting that created it. You can't perfectly exclude from finite amount of data that it might not have done this one. And this motivates something that in machine learning is called Bayesian Inference. It's not the only way to keep uncertainty estimates around. But Bayesian Inference surely is one of the famous ones, where you have a distribution. This doesn't work for some reason. You have a distribution over parameters after you've observed your data. So parameters in the L96 case is the forcing and the 3 parameters that are relevant for the dynamics. And the X in this case would be a simulation output. So you switch on the L96 simulator, you would use the forward version where you plug in a parameter set, and then you put in some form of randomness. In this case, it might be different initial initializations, different initial states for the solve of the differential equation. And then what this does is it gives you a forward probability density that, given for some parameter settings, there's a distribution over possible data that you could observe. So the resolved and unresolved variables in this case. And then what Bayes' theorem allows you to do that is to sort of invert the direction where you have started out with a forward model, which gave you the densities of the probabilities of data given parameters. And if you multiply this with this ratio, you get the probability over parameters given data. Now, how is this different to before? You get full parameter ranges that are consistent in some sense with your data, rather than just a single point estimate. We'll see in a second how this looks like in practice. Now, Bayesian inference is a fairly established thing. The particular in machine learning, the particular difficulty here is that for the L96, as I said before, the forward model is based on a solver of a differential equation. It's not a analytically tractable density that you can just query. Like, I have this data set X and I have this parameter theta, and given this parameter, how probable is this data set? So if you want to do this, apply this in this case and be able to quantify the uncertainties over your parameters given the data that you have, then you have to somehow work with the fact that this equation here, you can't even evaluate simply already because the likelihood term doesn't work. What Bayesian inference comes with also is a prior distribution, which encodes your prior beliefs over, for instance, sensible ranges of parameters. Like we've seen, the F parameter usually is set to 10, and you can say like it can be anything between 0 and 20, but anything outside of it. And if you don't care what it is inside, then you would go with a uniform distribution, for instance, for F between 0 and 20. Yeah. So why am I talking about this? As was advertised in David's email for today, one paper that we're going to look at now is Schneider et al. 2017. So you see the, this is kind of the main result figure of the paper, at least from my perspective, that you have these 4 parameters, F, H, C, and B of the L96. And you see these posterior distributions with uncertainties that they've obtained for a certain simulation as ground truth data. So rather than before, where we try to get a point estimate of the parameters, now you see that it's the orange thing that we're looking at. Now you see that if you simulate with the ground truth parameters, the classical one, F equals 10, H equals 1, C equals 10, and B equals 10, and you do a simulation and you try to recover this, then there is residual uncertainty over the parameters that you've used to simulate the data because of this uncertainty in the forward model. So, and what you can also see is that if you come in with a prior distribution that encoded our prior beliefs of where the parameters might have been, the posterior tends to be usually a lot narrower because it's conditioned in a probabilistic sense of way. It's conditioned. It's a conditioned probability over parameters, given the data that we've seen. Now, how do they do this? Just quickly jumping to the paper. As you can see, it's got lots of text. They're doing a thorough introduction into their way of thinking, interestingly enough, without using any of the typical notation, but introducing the new ones. Their own notation. And here we get to the part with the L96 model. This is our by now familiar equations for the resolved and unresolved variables. The way they go about constructing these densities is by constructing a energy function, J. So for every parameter theta, when you simulate resolved and unresolved variables, you compare that to data variables, which in this case, they show here with these little wiggles on top of the, you see that here, sorry, no, this doesn't want to, sorry. So this is the observed data in this case. So what they do is they create this energy function, which essentially is a Gaussian error over not directly the observed and unobserved variables that you simulated and those that you consider your data, but of some summary features that are reducing massively the dimension. So in this case, they chose 5 different summary features. So it's going to be the mean of the observed variables, the mean of the hidden variables, the unresolved ones, and then the squares of them, and then the inner product. They have some reasoning where these are informative about the parameters of the model, but I'm going to skip in the interest of time. But then what they essentially compute in order to give an energy function value to each parameter is that they simulate once from the parameter and then they compute from the simulation outputs. So the resolved and unresolved variables of the L96, they compute this fitness or distance function to the ground truth data. And how is this energy related to these probabilities? So here you see the potential energy for a given real observation for these different parameter values. So classically in I think in thermodynamics in many fields is you just do the exponential of minus the energy, and then you get the probability density after normalizing. So you see where the energy is particularly low, which means that the simulation results were very, very close to the summary statistics of the actual data. You have, in this case, you have low energy and then you have high probability. So with this method of essentially what is nowadays called, at least machine learning, likelihood-free inference, where they essentially construct, you could argue, a likelihood term for Bayesian inference from the simulations that they do. You can then use this for Bayesian inference and get these posteriors. In this case, there's an extra step of Monte Carlo that has to do that has to do with these other two terms in here that allow you to go from the synthetic likelihood that they just constructed to the posterior they want. Sorry. Yeah, there's also another paper for those of you interested. You can check this in the YouTube stream, I guess, of somebody. It's a Nature paper. It's a fairly well-known one, who has done essentially what Schneider et al. Did in 2017 for Earth system modeling, specifically for the general case. I would say it's at least very related. So machine learning knows this kind of algorithm as synthetic likelihood. Or if you're generous, approximate Bayesian computation. There's a whole field, as you will see in a second, and that also David and I were working a bit with in the past. So as David said, one final thing that I wanted to show that relates to this Bayesian approach that you see here is our own work applied to this model, which we did a few months ago when we first started the lab here. We applied an own method of ours, results which you can see here. I'm going to explain in a second what it does. So these are on the top diagonal, you see the marginals from Schneider et al. That it just grabbed out of their paper. And then on this lower diagonal, triangular panels, you see our results from our algorithm. So just if you just compare the marginals, so here on the diagonal you have the marginals of the 4 parameters of the I96 model. You again have the priors, and then in the samples we have our posterior. So these are the parameters that our approach believes goes with an observed simulation that is consistent with that. And as you can see, with a different method, so the posteriors over C, as you can see, ours and theirs pretty much agrees. But you can get, for instance, much narrower posteriors over the H parameter if you use a different method. And we haven't really validated whether our variances are perfectly on spot and if they're truly better. But the fact that the variances are small, and so the posterior uncertainties over the parameters are small, and we're still hitting the actually correct parameter that was used for generating the data, it's probably a good sign that something sensible is going on. Now, which method did we use here? It's something we worked on before that's called sequential or posterior estimation. It has this aspect that you choose a parameter from a prior. This is the top left box that we start out with. Then you do a bunch of simulations for your forward model, and then you want to regress essentially back into the parameters. But first of all, you do so through a neural network that doesn't just produce a point estimate of the parameters that may have produced a given simulated data set, but actual distributions over them. So these funny colored disks are supposed to be density levels for Gaussians. So if you're not coming from machine learning, it might be a bit harder to pass. And then once we have these conditional densities for every simulated data set, we can again plug in the measured data, and then what we get out once plugging in the measured data into the density estimator, we get out a posterior, and if we sample from that, this is where these distributions come from. And one thing that's cool once you go to the neural network density estimator is that neural networks are very flexible. They can take. So one thing you can do is, rather than follow Schneider et al. And take this data matrix and condense it into these 5 different summary statistics, which is just 5 numbers to summarize the whole data set, is you can just take this matrix, which is space by time, and just as we've seen before with the point estimate approach, you can just run a fully convolutional network on this that convolves some filters over both space and time. And why you could argue, so this is the posterior on the right is obtained with a network that just essentially eats the whole data and not just the 5 summary statistics as a bottleneck. And you can see that, for instance, if you look at the distribution of the C parameter, that we actually get posteriors that are sharper relative to if we just use the 5 summary statistics. This stuff isn't published yet, I have to say, so this is a bunch of tests that we should run to verify that all of this makes sense and this is correct, but I think this is some promising stuff that you could do. There's leveraging developments from the machine learning community that have been published in the last 1 or 2 years.
Marcel, there's a question from the Zoom chat from Eduardo. Are the panels in the graphical matrix the 2-dimensional probability distributions for each parameter pair?
Oh yeah, sorry. This is something I meant to say, but I forgot that. Yes. So on the let's look at this one because this is the left one because I think this is a very nice one. So on the diagonal you see the marginals, and then here you see the pairwise marginals. So in total, the thing is a 4-dimensional distribution, and given that it's not a Gaussian, there's actually a 3rd and 4th order interactions that might be interesting to look at. But just for visualization, and because people usually care about that, we show the marginals on the diagonal and then the pairwise marginals between 2 different ones. So here between the parameter f and the parameter c, or in this case log c. This is the distribution that we get from the posterior. And you can see cool stuff. If I just maybe quickly point this out, like you see, if we just use the 5 summary statistics, it looks like the parameter c isn't constrained if you just look at the pairwise, at the single marginal. But if you look at it in combination with the parameter f, is that if you know the value for f, so this is the, on the y-axis, you see the spread over c if you don't know the value of f. But if you know the value of f, then the spread becomes much, much smaller. So if you know that f is, I don't know, let's say around 1, then the spread of c is only on the top part. Well, if you know that f is, I don't know, what is this value, maybe 7, then the remaining uncertainty over c is only a 1/3 of that if you didn't know.
So I have one more general question as well. So then, I mean, what do you see as the major issues that have to be overcome to apply this kind of parameter inference to more realistic models in neuroscience?
Yeah, so one thing that is always a bit embarrassing to say about these models when you're talking to earth scientists and you come from machine learning is that in order to fit these posteriors, I generated 10,000 simulations because the network, it needs to be trained on many pairs of simulated data and parameters that were used to generate the data. It's a regression of a deep network in this case. I think it had in total something like 30 layers and a whole bunch of parameters. So there are ways to reduce the number of parameters, and this is actually in this figure that there's this little arrow in the center that goes back from posteriors into the model, which has to do with the sampling efficiency and the information content of the simulated data that you're producing. Like if you're generating parameters from a prior, you get all kinds of model behavior. But by the end of the day, you know, you will only evaluate the regression that you've learned at a single data point, which is the measured data. So if you had some way of knowing which parameters would lead to simulation outcomes of the L96 in this case that already look very close to the measured data, then you can learn the regression much more focused and with much less data. So it actually hasn't been our invention, but from a paper from Pablo Marcaris and Murray in 2018. And in the ABC literature, actually, even way before that, is this idea of going iteratively. So you generate some data sets from your prior parameters, and then you get a rough idea of the posterior, and then you switch to generating more data from the posterior. It's a bit tricky how to do this in practice because then densities change and probability densities don't like changing. And there's some conditions on them to hold, don't like being transformed. You have to correct for that. but yeah, long rant to your simple question. The big problem here is data efficiency.
So is that why Mouatadid et al. Only used 200 simulations? Because they want to simulate the scenario where you could only do 200 runs of a big climate model?
I'm not sure if this is what the intention was. They did say that they were generating only 200 because each of them needed to be very long, because these are chaotic systems, and you want to make sure that they first of all have enough time to diverge, and that you get to see the full repertoire of the dynamics. Whether they really anticipated this to be realistic for the number of simulations, I don't know. But it is right that what you're, I think you're pointing out here is that you might go with much fewer simulations if you're able to use an individual simulation of a climate model as multiple data points, like chunking up across time, or if you have a global model, maybe chunking up across space, learning from different parts of the world to map back into the parameters of a global circulation model.
All right, thanks a lot. So we saw this model. We saw one thing it can be used for as a test bed for inferring the parameters of a simulator, right? So given these unknown model parameters which determine the outcome of these simulations, can we use this as a way to test our ability to identify what those parameters were from data? So now I want to show, I think this will be very brief, but I think it's quite an interesting scenario. So this is the paper to go with the blog post we looked at earlier from Stefan Rasp, and it covers a lot of things. I recommend reading it. He kind of lays out a vision for how to train machine learning parameterizations together with Earth system models. But I'm going to cover just one aspect of it from this paper here, which is the concept of a parameterization in earth science and how this can be done with machine learning, right? So we have our Lorentz equations as before, right? We have our slow variables, and they're affected by the fast ones. We have our fast variables, they're affected by the slow ones. They exhibit forgetting properties, and they conserve other quantities as well. So the kind of parameterization Rasp is talking about in this work is the idea of, what if we didn't want to simulate all these fast variables every time? We wanted, having done some simulations where we simulate the fast variables y and the slow variables x, we want to come up with a quick way of guessing the effect of the fast variables without actually having to spend all the computer cycles simulating them. So to give an analogy back to atmospheric science, and this is a very common feature of general circulation models in climate science and weather prediction, we'd like to know the effect of convective processes, cloud formation, precipitation, which comes down to these tiny scales, microphysics, ice crystals, water droplets, and clouds tumbling around in turbulent air. We can't simulate that on a global scale. It's not possible now. It won't be possible probably in 20 or 30 years with our quantum computers that we'll have then either. But what we can do is do these simulations on a small scale and then try to learn the average effect of these small unresolved processes on the processes which can be resolved in our grid cells, however many we're actually able to use on our clusters when we do these big simulations. So effectively, what one is wanting to do and what is modeled in this simple mathematical framework here is we want to know the effects of the y's on the x's. So given all the x's, or given rather each x individually, I want to say what is the likely value of the y's and what will be the likely effect on the change of the x's in time. That is, if we don't explicitly model and resolve with these expensive computations, if we don't resolve the fast variables, can we guess the effect they would have had if we did model and resolve them? And in this paper, there's two ways of doing this to discuss. So first, to generate training data. In either case, you have to run the fast and slow variables together in the full 2-level Lorentz 96 simulator. But then having done that, you can plot, if we look at the blue points here, we can say, here's the value of a slow variable, and then this is the effect of the fast variables on that slow variable. And it's not at all surprising we see a correlation here, because these fast and slow variables are coupled. And then what they want to do is essentially learn a curve that describes this relation. We can do this in the solid orange line. We fit a line to it, and we actually get a pretty good fit. In the green line, we can see if we use a neural network instead to predict the effect on the rate of change of the slow variable from the unresolved fast ones, we get the green curve, fit with a neural network. And this is basically a way of using the Lorentz 96 model as a test bed for various approaches, in these cases simple, deterministic, not too complicated ways of predicting the effect of variables which we cannot afford to resolve all the time. And then of course one can run simulations, and one can see the effect of doing these various approximations on, does it introduce a bias to the results of the simulation? Does it introduce a lot of errors? How can we couple this together with online learning to correct any long-term errors? So this is what's proposed here as a simple way of using data-driven approaches, linear regression, or if you want to be fancier, not a neural network, to predict the effect of the variables we can't resolve. So one more point from the blog post that I think Stefan really rightly makes, which is that, part of the problem here is that the parameterization is too good. One is able to get a really good fit for the effect of the fast variables from the slow variables. So this is not really the case in an atmosphere, a detailed atmospheric model. Just because the average moisture, temperature, pressure doesn't mean you can guess what convective processes are happening. So the argument here is that this may be too simple of a model to really reproduce the core computational challenges that arise in atmospheric science, and maybe we need more complicated models. He kind of gives a brief sketch of what that might look like, and I'll link the blog post in the YouTube comments as well. So this is a basic concept of parameterization, and the idea, just to encapsulate one more time before I hand over to Tobias for a more advanced version of this, is we don't model the fast variables, but instead we guess what their effect would be from the state of the slow variables. Okay, so Tobias, if you want to take over now, Tobias is going to talk about a kind of a more sophisticated, particular approach of doing this parameterization process, of approximating the effect of the slow variables from the state of the fast ones.
Yeah, thank you, David. Yes, I will start to share my screen. These are the two normal Lorentz equations that you saw already half an hour ago. So and in a parameterization, we want to parameterize the impact of these fast scale variables on the slow scale variables, and we want to parameterize these variables given these slow scale parameters. And this is already done for weather forecasting. For example, the ECMWF uses these techniques, for example, already. So in this paper that I want to present, they propose to learn a stochastic parameterization, so that this parameterization that I've shown here, this u value isn't only dependent on the slow variables, but also on a noise input, so such that this u variable can cover the whole PDF of what is possible with a given x value. So and for example, the ECMWF use already stochastic parameterizations. So there's a quite simple way to do stochastic parameterization. It's called stochastically perturbed parameterization tendencies. So basically, for in a numerical weather predictor or a numerical climate model, you are parameterizing physical tendencies on the large scale variables. So for example, on the temperature, on the wind, on the humidity. And then in this SPPT scheme, they perturb these tendencies randomly with a in this case with a random number drawn from a distribution between minus 0.5 to 0.5. So and as I said, they randomly perturb this, and then it is, for example, possible to run an ensemble of weather forecasts with this, or it is especially used for ensemble forecasting because the normal problem for ensemble weather prediction is that the ensemble is under dispersive. This means that the ensemble cannot capture the error growth of the real forecast error, so such that the ensemble spread is too small compared to the forecast error. And they've shown it also quite nicely over here. So so basically these lines here on the top are the errors, and these lines here on the bottom are the ensemble spread. And if you for example in the tropics, if we for example compare the model without stochastic parameterizations, then we can see that the error is this gray curve here, and the ensemble spread is this curve here, and we see that the ensemble spread is very much under dispersive. So I think at the beginning the ensemble spread is 0.1 or something like this, and the error is 0.5, or so it is 5 times higher than the ensemble spread. And if you use stochastic parameterizations, then it gets better because the model is randomly perturbed. And in the so with this scheme, the effect in the tropics is larger than in the exotropics, because the tendencies are larger in the tropics than in the exotropics. So this is more effective in the tropics, and this is why we need another technique to disturb, for example, to do a stochastic parameterization. And then also there's a need for stochastic parameterizations in climate models, because, for example, here this is an overview paper from 2017, which is quite well known in the stochastic parameterization community, I would say. So and here, for example, if we have a stochastic parameterization, or let's say if we have a deterministic parameterization, and we have a climate system where we have two local minimums, then it could be that if we are using a deterministic parameterization, that the climate state stays in one local minimum, despite the fact that there's another local minimum. And if we increase the stochasticity, then we can also cover the second local minimum, and then we get, for example, in this simple example, a B-model probability distribution, which captures more of the real climate or the real effects on the climate of for example of a solar forcing, and then so this is called noise-induced transition, and then also there's another effect if we have an unimodal potential, and then we have no additive noise but multiplicative noise, so such that the noise is dependent on the state. Then it could be, despite the fact that we have only one single minimum, that we get a multimodal probability distribution due to this state dependency, and this is then called noise-induced shift. But yeah, so let's say stochastic parameterizations are used to capture uncertainties which are within parameterizations. So because of course parameterizations aren't perfect, so we need in some kind to introduce uncertainties into the parameterizations, and this is done with stochastic parameterizations. And then the paper that I want to show, they are using these generative adversarial networks that were already presented last week, and they try to parameterize, as I said, these fast variables, and they want to parameterize these fast variables with the slow variable at the time point before, and the tendency or the coupling. So the U is this parameterized effect in Stefan Rest blog post. It was, I think, called B. So here it is called U, and they try to predict this U at time t based on the slow variables at time t-1 and the tendencies at t-1. So and as I said, they are also using a random vector, a random input vector to introduce the stochasticity, and then they have so this is the architecture that they are using. So they have a generator which is in some kind of forward model, which parameterizes these U variables, given, as I said, the slow variables and the previous tendencies, and then they have an input noise, and then the output here is called V, but it is U at time t, and then the discriminator, so the second neural network tries to discriminate between the generated U and the true U. So and the true U can be calculated with this formula in the Lorentz 96 model, because this Y is dependent on the slow variables, and so it is in some kind of a delayed effect of slow variables on other slow variables. So they can actually calculate this U, and then the discriminator tries to discriminate between the generated U and the true U, and because it is a conditional generative adversarial network, they have to give the input U and the input X also to the discriminator, and this is the network that they used. So it is quite interesting to see this network because they add Gaussian noise before every hidden layer, also for the discriminator, and then they try different variable different magnitudes of noise for these hidden layers. So and they've done many different experiments where they use different noise magnitudes, different input variables. So for example, here, if it is called XU, they're using as input variables the slower variable and the tendency, or for example, if it is only an X, then they use only the slow variables. And then also they played a little bit around with different noise correlations. So here they are adding Gaussian noise to every hidden layer, and this Gaussian noise can be either white noise, so temporarily independent, or it can be correlated noise, so-called red noise, and they model this red noise with a RR1 process. So with a, let's say, with a, how is it, RR? It's an abbreviation for what? So with a RR1 process. So to compare white noise and red noise is dependent on the time, and white noise is not dependent on the time. And then also they try to deactivate the noise in the last layer here. So they have how many experiments? 8, 12, 16, 20 different experiments, and they trained 20 different generative networks, and then they compared these generative networks to a polynomial regression, so to a cubic regression, which is in some kind the state-of-the-art parameterization for the Lorentz 96 model. So, and then they, for example, so then they evaluated the stochastic parameterizations in 3 different ways, or 4 different ways. So as a first step, they tested their parameterization with their offline data set, so with the training data set. Then they imitated in some kind of weather forecasting, and as a third step, they imitated climate prediction. And then in a fourth question, they asked how closely the GAN can represent the switch between different regimes in the Lorentz 96 model, but I will not cover this here. So as I said, they started with an offline testing, and here they show that this is the so-called Hellinger distance. So it's in some kind it's a distance between probability distributions, and it is the distance between the probability distribution of the forecasted slow variables to the true variables. And so if the Hellinger distance is, I think, if it is 0, yeah, if it is 0, then there's no difference between the forecasted PDF and the true PDF. So and they show that in the training data set, or in the offline data set, they are better than the polynomial regression. So the polynomial regression is this dotted dashed line here. So and especially here for this offline data set, I've marked it here. This run was quite successful. So it is a run where they had as input the stow variables, then the old tendencies, noise magnitude with white noise. So I can on top so a noise magnitude of 0.1 standard deviation of 0.1 standard deviation, 0.1 standard deviation, white noise, and then output layer noise. So this is the And also, what they noted here that there's some oscillation in the Hellinger distance for different runs, and this is in some kind one of the problems of GANs, because GANs are because it is a minimax game between two players, and so there are problems with oscillations for GANs, and so this seems to be like a normal problem for GANs. So, and then they've done almost the same that Stefan has done. So they plotted the histogram of the tendencies independency on the slow variables the time step before, and this is the true PDF, and these are the approximated PDFs. And what we can see here that the polynomial, I think this on top here on the top right side is the polynomial regression, and the polynomial regression works quite well in this sense, such that the histogram is well captured, or the probability distributions are well captured, and then for most of the GANs it works quite well, but they have in some sense some problems with showing values which aren't plausible. So this is especially the case in these three configurations, and this is so these three configurations are with red noise. So red noise seems to don't work so well in capturing the PDFs. So
I'm sorry, Tobias, can I interrupt and ask a question?
Yeah, of course.
So is this the error introduced by the GAN parameterization for a single step forward of the algorithm, or is the error that kind of accumulates over a longer time?
I think this was for this offline, and this is only for a step forward.
So this means basically if we look at the overall prediction of the effect of the fast variables and the slow, this is how much error we introduce at any one time point. But then I think it would be a very interesting question, whether we're thinking about Stefan's criticism of the linear thing being too simple, or these more sophisticated models here. The real question I wonder is maybe what does this do to the overall doubling time of the model and its predictability?
Yeah, so I think this is a little bit covered in the evaluation of weather forecasting. So this will be the next subsection, because they've done something like this here. So this figure looks a little bit messy, I think, but so this is they've plotted the RMSE and the spread in dependency on the MTU. So it is the MTU. I think it is the doubling of the error. No, not doubling. It is the it is the time unit of the Lorentz model, and 2 MTUs are roughly 10 atmospheric days, as written down here. And so basically they are showing that it works quite well, but there are some models where the error is exploding. So these two models are the models, I think. Yeah, these are the two models where only small additive noise is used, with either red noise or white noise. It doesn't matter in this case. And this is and also is for small noise and the u input vector, and so as input they used x and u, and they say that this is the case because the errors are propagating for or are exponentially amplified, and so this is the case if you use a, so if you are not using enough stochastic noise and also using as input the tendencies, then you get this error explosion. I hope this answered your question.
Yeah, absolutely.
So and they've also shown here that this light gray line is the polynomial regression. No, this is the polynomial regression here with the star. And they've shown here that, for example, that this model here, the second model on top, this is yeah, in some sense better than the polynomial regression. But as I said, this figure is a little bit messy because they compared here 7 different RMSEs, including the spread, so 14 different lines in one figure. I think this is a little bit too much. So as I said, they compared then the ensemble spread. So they did an ensemble forecasting and then estimated the root mean squared error of this, so of the ensemble mean compared to the truth, and then compared this with the ensemble spread. And this line over here is the polynomial regression. And they show that some of the GANs are better than the polynomial regression. Some are almost equal to the polynomial regression. So all in all, that the GAN can work for weather prediction. And then they estimated also the Hellinger distance between the PDFs. So they use the RMSE to estimate a metric for weather forecasting, and the Hellinger distance as a metric for climate prediction. How well the PDFs for climate predictions are matched, and here we can see that so if stochastic parameterization is quite good for weather forecasting, it is also quite good for climate prediction in this case. So, but also they plotted the PDF. So this is the climate PDF. So the PDF, and over all x values and all time steps, I think. Yes, it was over all time steps. And the black line here is the true PDF, and the other lines are our parameterized PDFs. And we can see that for, as I said, for the input with the so for a U input or XU input and small noise, it doesn't matter if one uses white noise or red noise. So in this case, if the noise is too small, then we get only an unimodal distribution. And in all other cases, we get this weirdly shaped distributions, and also so dark gray line here is the polynomial distribution. So this is the difference between the true PDF and the modeled PDF. And as we can see that there are some GAN parameterizations which are better than the polynomial distribution in capturing this PDF. And also they've estimated the spatial correlation between grid points. So as David already said, the Lorentz 96 model, the variables are on some kind of grid points, and so one can estimate the spatial correlation of it, and we can see if the PDF is matched, then also the spatial correlation is matched quite well, and also the temporal correlation. But there's in some kind of a shift because the temporal. So this is the temporal correlation, and 1 MTU is around about 5 atmospheric days, and we can see that almost all parameterizations are a little bit shifted compared to the true temporal correlations. But there's one GAN parameterization which has this lag in it, but the magnitude of the temporal correlation is a little bit too small. So this is this indicated model here, and then they've done also some work in comparing the wave numbers of the Lorentz model with the parameterizations and so on. So they did in some sense four different steps in evaluation their GANs. So they, on one hand, they evaluated the GANs with this offline metric. Then they evaluated it for weather forecasting. Then they evaluated them for climate prediction, and then for this with these wave numbers and regime switching. So they concluded that these GANs parameterizations seem to work quite well, and that they are competitive with polynomial regression schemes. But there's a problem because here on the left hand side we can see for all 20, I think this was for all 20 parameterizations that the RMSE, the weather forecasting RMSE, is very much correlated to the Hellinger distance for climate prediction. But if we compare the Hellinger distance for offline evaluation, or estimated in this offline data set, with the RMSE to spread ratio for weather forecasting, then we can see that there's this was it, that the climate Hellinger distance is not correlated to the offline Hellinger distance. So this means that if we say that, for example, this model indicated here, this XU medium noise magnitude with white noise, so this model down here doesn't seem to be the best model for weather forecasting, climate prediction. So the distance or the matrix for the offline metrics for GANs are not do not say anything about the forecasting error or something like this. So they are not correlated, and this is in some kind of problem. And then they conclude with four different main points. So the first main point is, as I said, that including the tendency from the previous time step provides a natural approach for building temporal dependency. into the parameterization, but it can lead to accumulation of errors in the forecast, such that local and time parameterization should also be considered. So this means that the error is accumulated and exponentially magnified. And then also one challenge is that they've written that it is possible that the noise characteristics could also be learned by the GAN framework to automate the tuning of the stochasticity. This means that they're using here in some kind not a deterministic framework, but a frequentistic framework, and which kind of noise it needs. So, but all in all, they conclude that for this Lorentz 96 model, it works quite well, and that it could be a step forward for stochastic parameterizations to learn it based on generative adversarial networks, without the need of hand, let's say, creating some parameterization rules by hand. So
that's a really impressive level of detail and really interesting results. They really looked at a lot of different aspects of this, and I think maybe that could be some useful guidelines when trying to develop more, realistic parameterizations for realistic models.
Of course, yeah.
I think in the interest of time, because we're already fairly over, we should open up to general questions. I have one or two more points about the main paper, but I'm going to skip them for now. If anyone wants to ask a general question about any of these papers we covered, either in the YouTube chat or the Zoom chat, just go right ahead. Maybe Tobias, if you
go, yes. Sorry.
Please.
I'm Johannes from the KSD department. Mm-hmm. So we are also doing a little bit of work on data assimilation. And I have one basic question, terminology, because I think this term...
I called it a diffusion term. That's absolutely a mistake.
But it appeared also in I think in one of the later papers. Maybe this is just passed on. There
is a concept of diffusion in terms of like this advective process where things move around, but where did you see it? In which paper?
No, I think wasn't it in the second or third presentation? There was also I saw the equation, and then it was passed on from paper to paper. No, it was and it was not handwritten, so I just thought it was in the presentation. Somebody also showed the Lorentz equation, and there was a bracket below the minus x term. But I think this is it's not important. But I was just a little bit confused. But in my view, there is no diffusion in this Lorentz model. Yeah. This minus x term is just a sink. I mean, it's an energy sink, so energy is extracted. This is what we would call dissipation, I think.
Yeah, that seems exactly right.
The second question I had was, the number of parameters in the Lorentz model is, of course, relatively small. And I mean, if you compare this to realistic problems, for example, we are when we look at ocean models, for example, looking at things like bottom roughness in the German Bight, which is very uncertain. And so there's a really very big number of unknown parameters. Hundreds to thousands of unknowns. So one question is, how realistic is it to apply the techniques like you described here to these larger dimensional problems? That's one question. The second question is, if you have a problem with the dimension that's small, so what you discussed here, of course, you could also think about applying more traditional methods for optimization. So you mentioned that if you have advection, of course, it's true. This is not differentiable, but of course there are also optimization procedures which do not assume that the function is differentiable. So including also ensemble methods. I think there's one method called ensemble smoother, which was also used in the past for a parameter estimation. It also has some limitations, of course, with regard to linear properties and so on. But I think basically the question I had was, is there a kind of benchmark testing for you where you say, okay, we have to beat, let's say, this classical method with this machine learning approach for us to make sense? The last point was, it was coming to my mind that, again, coming back to this non-differentiable property of the advection term, because I'm also fighting a little bit with this. I'm also working on 4D var schemes where you actually try to use the gradient of this thing. It's also true, I think, that in the vicinity of the true solution, this thing is still has some smoothness properties. The problem with the non-differentiability comes in when you start quite far away from your solution. And then in the case of the ocean models, the problem that you have is if you change the parameters so much that actually the current vector, then you're really in trouble with regard to these non-differentiable properties. But if you're already quite close to the solution, you can in fact apply, let's say, standard or more traditional methods which are based on gradients. And it was just coming to my mind that maybe one could somehow combine the two approaches to use machine learning approaches to get relatively close to the solution, and then in the end to do the fine tuning with maybe gradient type of solvers. And then just the final point I had was, I think this Lorentz equation or this Lorentz model, it's quite nice because it tries to look at these two different scales. And I think the main idea behind the approach here is that the idea is that the high or this fast scale solution is basically also attributed to a smaller spatial scale. I think that's the idea behind it. So we have a very small scale, which is not resolved, which is also taking place on a faster temporal scale. But it was also coming to my mind, we are also working on coupling, for example, between the ocean and the atmosphere, where we also have a coupling problem. So we have two systems with different scales, but it's a little bit different because the atmosphere is not included in the ocean, but it's interfacing with the ocean in different ways. And so I thought maybe one could also apply similar kind of tools also for these sort of problems, because that's also what we have to face in when we do assimilation into coupled ocean atmosphere model. You're also facing problems like this. Yeah, this is what I wanted to say. And so thanks again for the interesting presentation.
No, thanks a lot for participating. I could say a little bit about what my limited knowledge is on one or two of those points, which is I do think that it's much more of a challenge when you want to estimate many parameters at once. And I think this is also why it's very nice to have differentiability, that these methods based on gradients like what we use to train neural networks really do scale to millions of unknown parameters and work out pretty well there. I think there are methods, maybe ensemble methods, maybe other methods based on rejection, from all across machine learning, statistics, and I think some very domain-specific stuff too, which is maybe worth covering in the future. It works well, but I think it's going to be difficult to scale up to many parameters without either neural networks or some other kind of gradient-based approach. I do think if you mention an example where you're talking about parameters maybe across the ocean bed, if I understood correctly, if these have a spatial structure, then maybe you're able to kind of see some repeating spatial structure in the problem, and maybe convolutional networks or similar things would help you to exploit the regularly repeating structure, and maybe this helps you with your problem. These are all very interesting points. I think we only have partial answers to them. There's another question in the Zoom chat for Marcel asking if the density estimator is somehow tailored to the Lorentz model or if it could be applied to other models as well. Sorry, Tobias, I'm going to take over the screen share again.
Okay.
Yes and no. It's not specific in the sense of the kind of layers that we're using. So for the Lorentz case, we had two applications. One from summary statistics, which is mapping 5 numbers into 4, and then we went with some fully connected network. It wasn't just a network; it was a normalizing flow because it needed to produce not just the point estimate, but it needed to produce a full distribution over stuff. So yeah, I mean, and I guess in that sense, it is a special network, and that has to be a network that gives a conditional density in principle. But for instance, when we switched then to feeding in the full data matrix, which is space by time, we just prepended a bunch of convolutional layers that were reducing the signal as we went up in the layer up to the point where it was, again, just a handful of numbers. And then we stacked the same architecture on top of that we had if we were just using the 5 summary statistics. So it's a machine learning data analysis problem. You have some input numbers of a certain dimensionality and some output numbers, and you go with that, at least as a first start.
So we have time for maybe one more question or comment. I'll see if anyone wants to add something in the chat. While I'm waiting, I'll just point out one very interesting thing from the conclusion of the original paper, which is that, Lorentz, he talks about these different spatial scales. He starts off, he says, okay, the fast scale might be clouds or storms. The slow scale might be more of a global or local, over Europe, over other continents, the atmospheric state. And then he says, okay, what if we go an even longer time scale and bigger spatial scale, and you begin to talk about things like ENSO, or the quasi biennial oscillation, or these things over a couple years. That are consistent and seem to have a memory in the system. And he asks, what if you keep going? The overall set of the climate itself, the set of repeating patterns that it contains, the set of features it contains, this itself can change over centuries. And what is the coupling between this very, very slow process and the faster ones? Which direction is the arrow of causality pointing? I don't know if we have any better answers to this today, but maybe someone with more expertise can chime in. I think it's a very interesting, provocative question. Okay, well, we've covered a lot of material. Thanks everyone who participated, and those of you who made it through the whole thing. We will do this again in 2 weeks. And thanks everybody.
Thanks.
Thank you. Bye-bye.
Bye.
Bye.
Bye.